Okay, maybe we can start. Good morning, everyone. Today we have one of our own, Dr. Alper Erdoğan, who is a professor in the Electrics and Electronics Engineering Department at our university. Let me briefly talk about his background. He received his BS degree from Middle East Technical University in 1993 and his master's and PhD degrees from Stanford University in 1995 and 1999, respectively. Before joining to Koç University in 2002, he worked as a principal research engineer at Globespan Corporation. His research interests include adaptive signal processing, machine learning, physical layer communications, computational neuroscience, optimization, system theory and control, and information theory. He was an associate editor for the IEEE Transactions on Signal Processing and also a member of the IEEE Signal Processing Theory and Methods Technical Committee. And today we are lucky to have him to hear about their recent work on Polytopic Matrix Factorization. Thank you, Alper Hocam. The stage is yours.
Thanks a lot, Aykut Hocam. Thanks a lot for the introduction and invitation. So in this talk, I will try to introduce a recent flexible matrix decomposition method, unsupervised matrix decomposition method that we refer to as polytopic matrix factorization, and some connected topics, which is mainly actually the unsupervised learning using an information-theoretic criterion. So let me, go through the outline. So this is, at the beginning, I will briefly talk about what a matrix factorization problem is, mainly from the point of view of linear inverse problem, and then introduce polytopic matrix factorization as a solution to the matrix factorization problem, and introduce the information maximization principle that we use in connection with the polytopic matrix factorization, and then talk about some of the extensions of this work that we are currently working on. For the matrix factorization problem, we can start with the famous problem in linear algebra, which is system of linear equations, which is basically, we know the vector y and matrix H, and we try to obtain S. So this is the linear inverse problem. And if there's a solution, we can obtain it through different means using Gaussian elimination and so on. We can make this problem a little harder if we assume that H is also unknown. So if y is given, but H and S are not given. So if this is the case, then there are like infinitely many solutions, because we can pick H as first column Y and so on. So we can actually produce many H and S components. But if we view this as a linear mapping with some input S and output Y, and if we have like multiple outputs for different inputs for the same linear mapping, and if assume that we have n such outputs corresponding to n different inputs, we can organize that in the form of a matrix multiplication where y's are the known outputs and H is the linear mapping that we don't know, and S are the inputs that we don't know. So I'm sort of introducing matrix factorization from the point of view of the inverse problem. So here we are given Y matrix, and we are asked to find H and S matrices. So therefore, we can actually sort of summarize this as we are given a Y matrix, which is supposed to be a multiple of, in the generative model, HG and SG matrices. So these are the generative model matrices. So we would like to obtain them from the original Y matrix. In order to obtain uniquely this H and S matrices, original HG and SG matrices, we need to make some assumptions on the data model. I guess I need to sort of zoom out. So some of the assumptions that are available in literature that enable this unique factorization are basically independence, which leads to independent component analysis, non-negativity, of H or S matrices, which leads to non-negative matrix factorization. Sparsity, which is typically imposed on the S matrix. So that basically leads to the sparse component analysis. And anti-sparsity, which means most of the vector elements are close to their maximum values. That is basically can be considered within the context of bounded component analysis. So I will shortly go over these existing approaches and then introduce our approach. So in the independent component analysis, we assume that the columns of the SG matrix are drawn from a stochastic source whose joint density is a separable PDF. So here there's a toy PDF here, which for the two-dimensional case. So this joint PDF is basically a separable PDF, which is a product of the marginals. And we assume in the independent component analysis case that the columns of this S matrix are drawn from the domain of this stochastic source. And this was actually independent component analysis was introduced in the context of neuroscience, basically for modeling the sensory processing in the nervous system by Herold and Uten. And they basically show that the independence is a sufficient condition for a recovery of H and S matrices in the asymptotic case, actually, when we take n go to infinity and so on. So the later approaches that I'm going to introduce are deterministic approaches. They don't make stochastic assumptions about the model. So, for example, non-negative matrix factorization makes the assumption that the columns of the S matrix comes from the non-negative ortant. So that also is an identifiability enabling assumption. For example, if you assume that these non-negative ortant samples include these coordinate axis vectors too of various lengths, but we should have some vectors with all zeros except one location. So under that assumption, Donovan and Studden showed that you can actually obtain the original generative model HG and SG up to some basically allowable ambiguities in terms of permutation and scaling. But that's sort of a restrictive assumption that you need actually exact coordinate axis samples within your S matrix, which I will show that it was sort of then replaced with a weaker assumption. Another actually extension of the non-negative matrix factorization is called the simplex structured matrix factorization. So here the vectors are actually non-negative, but they're also actually, they have unit L1 norm. So they are basically sum up to 1. So this is also called the probability simplex because the points in this simplex are PMF, probability mass functions. And again, this set also enables identifiability. If the vectors, S vectors are coming from this set, we can identify our HG and SG up to some permutation ambiguities. Given that, for example, these vertices are available in our data set. So that assumption is called, if the vertices are available, it's called separability assumption or local dominance assumption, but it's a sort of a strong assumption. Later, it is replaced by a weaker assumption. If you consider this unit simplex in the three-dimensional case and the second order cone, the intersection of the unit simplex and the second order cone is this disk region. So we are looking at this unit simplex from this direction. So you can see the cone here. So Fu, Huang, and Sideropoulos recently introduced a new criterion for basically identifiability, which they call sufficiently scattering condition. If the samples are such that their convex hull contain this cone intersection region, and basically there is a condition about also the tangency. So basically this convex hull is tangent to the border of this sphere here only at the points where the original polytope is tangent. So under that condition, you can show that you can actually recover your HG and SG matrices up to, again, some permutation ambiguities. So another set that is known to enable identifiability is the L1 norm ball. So if you refer to actually these S vectors as latent vectors in the matrix factorization framework, or feature vectors, because this is a linear decomposition framework. So if this assumption that these vectors are coming, these latent vectors are coming from the set, is corresponding to the assumption that we are assuming that they're sparse, or we can actually reflect sparsity assumption by assuming that those vectors to lie in an L1 norm ball. And there are actually many results about sparsity and basically sparse decompositions. In particular, within the bounded component analysis framework with my student Eren, we showed that if you include these vertices of the L1 norm ball inside this matrix, you can again guarantee identifiability, which is again sort of a strong assumption, but we will replace it with a weaker one in this talk actually. So another set that is known to enable identifiability is L-infinity norm ball. This basically corresponds to anti-sparse case. This is the dual of the L1 norm ball. Here, if you consider, for example, the vertex points, they correspond to the vectors that have achieved their maximum values. All the components achieve their maximum magnitude values. So that's why it's referred to as anti-sparse case. And it turns out that it's a good representation for example, digital communication signals, as well as some natural images. And again, for this set, identifiability is guaranteed. We have shown that if the vertices are included inside this matrix, original SG matrix, together with my student Hussein. So just to summarize, we are interested in obtaining the original factors from a data matrix Y, and there are some sets besides the independent component analysis. Basically, membership to these sets for the columns of SG enables identifiability, such as non-negative orthant, unit simplex, L1 norm ball, and the L-infinity norm ball. So the question that we raised is, can we find some other domains for the latent vectors that enable identifiability? And the second question that we address is, given that that set leads to identifiability, what is the condition for selecting samples from that set? Because you cannot really take arbitrary samples. These points that you select from the set should reflect somehow this set's structure, because that's the one that you are exploiting in the matrix factorization process. So for the first question, which sets enable identifiability beyond these four? We looked at actually these two polytopes. Polytope is a polyhedral set. It's a bounded polyhedral set, which is intersection of half spaces. So you have phases and so on, but it's a bounded set. So we have these two polytopes that enable actually identifiability. So we basically were curious if we can find some other polytopes that enable such identifiability for the matrix factorization. And in fact, we refer to this factorization framework as the Polytopic Matrix Factorization, where we have the linear generative model, where HG is assumed to be a full column rank matrix. So it's either it's a tall or square matrix, but we are also working on the fat extensions of this, which is the undercomplete case. And the columns of SG are drawn from a polytope. So that is what we call refer as the Polytopic Matrix Factorization. And to obtain the factors, I will explain this, but this is essentially the criterion that we use, that we actually inherited from the non-negative matrix factorization and bounded component analysis. So here, we are trying to obtain H and S. So the optimization is over these factors that we are searching for. And we define actually the sample correlation matrix for the columns of the S matrix. So this notation is for the columns of the S matrix. So RS is the sample correlation matrix, and we are trying to maximize the determinant of the sample correlation matrix. This refers to an expansion of the samples. If you consider this to be covariance, you can actually replace by the covariance too. The eigenvalues of this matrix are the variances in the principal directions. The determinant is the product, and that determinant of the eigenvalues, those variances, is referred as the general variance. So we are trying to actually, by doing this optimization, we are trying to spread the samples, but the samples are assumed to be inside this polytope. So therefore, they're restricted into a compact space. So we are trying to spread those samples inside this polytope. So that is the goal. And this optimization process assumes that the original SG matrix columns are spread inside our polytope, so that if they basically are localized in some region of the polytope, they are not really representative samples. But if they are basically spread and reflect the basically boundary structure somehow, they basically reflect the shape of the polytope. But we have actually a quantitative way of determining whether the samples of SG are spread sufficiently across the polytope. For that, we use a geometric approach and introduce the use of what is called the maximum volume inscribed ellipsoid of a polytope. Okay. So what is that? So suppose we have this infinity norm ball. The maximum volume inscribed ellipsoid is a unique object lying inside, it's a unique ellipsoid lying inside the polytope, which has the maximum volume. Okay, so this is basically unique for each polytope, and you can obtain it through some convex optimization problem solution. So for a L infinity norm ball, it's essentially L2 norm ball, which is a sphere. For more interesting example, this is a new polytope that we haven't really covered up to this point. But if you consider the intersection of the L1 norm ball, which corresponds to sparsity assumption, with the non-negative orthant, which corresponds to the non-negativeness assumption about the latent vectors, then you obtain actually a triangular region in the two-dimensional case. And if you calculate the maximum volume inscribed ellipsoid, it's not spherical anymore. It's actually an ellipsoidal shape. Okay, and in the three-dimensional case, it's a nicer picture like this, where you have this maximum volume inscribed ellipsoid is sitting here, which is this black solid object. So we use this maximum volume inscribed ellipsoid in order to determine the sufficient spread of our samples relative to this maximum volume inscribed ellipsoid. So you can sort of consider maximum volume inscribed ellipsoid is an ellipsoidal approximation of the polytope. So we basically compare our samples against this maximum volume inscribed ellipsoid. So the sufficiently scattered condition that we proposed is basically consists of using this maximum volume inscribed ellipsoid. So it's basically has two components in it. The first component says that the convex hull of the columns of SG should basically contain the maximum volume inscribed ellipsoid of the polytope. So just to explain this, the red curve that you see is the boundary of the L1 norm ball polytope. And the blue points are our samples that we take from this L1 norm ball. So according to this condition, so this black circle is the boundary of the MVIE, maximum volume inscribed ellipsoid. So according to this condition, my samples, convex of hull of my samples should contain this maximum volume inscribed ellipsoid. Okay, so in a sense, these samples should be so much spread around inside the polytope such that their convex hull is a better representation compared to the maximum volume inscribed ellipsoid, because it covers more area inside the polytope compared to the maximum volume inscribed ellipsoid. And there's another condition which I will skip discussing, which is in terms of the polar domain of these sets. But I can briefly say that this condition imposes that our convex hull of our sample points should only be tangent to the boundary of the ellipsoid, only at the points where the original polytope's boundary is tangent. Okay, so as you can see in this picture, our convex hull is not really tangent at any other point. So this means that we want our points to be spread inside the polytope such that their convex hull contain the maximum volume inscribed ellipsoid, but it shouldn't be arbitrarily tight. It shouldn't be tangent at arbitrary points. So that is the second condition. Okay. So using this condition and the Det-Max criterion, which is this, we can actually give identifiability proofs for different polytopes. For example, for the infinity norm polytope, I think it's hardly visible. So these points are examples of three-dimensional infinity norm polytope sufficiently scattered samples. So you can see that we no longer require that we include vertices in our samples. So this is sort of more plausible from the practical point of view. And their convex hull contains the sphere, which is the maximum volume inscribed ellipsoid. We can give a theorem that, sorry about this. We can give a theorem that the solutions of this Det-Max criterion, by the way, this is actually a joint work with my student Gökcan. So we can give a theorem that the solutions of this Det-Max criterion provides us with the original factors with HG and SG with some ambiguities in permutation and sign. So we can recover our original samples, original HG and SG matrices with these ambiguities. And we can actually give a similar theorem for B1. So if the samples are sufficiently scattered inside this L1 norm ball, and then the solutions of the Det-Max criterion will be basically our original HG and SG matrices, again with some ambiguities in permutation and also sign. And we can do the same thing for B1 plus, which is the non-negative sparse case. So in this case, again, the solution, if the samples are sufficiently scattered inside this polytope, we can obtain our original HG and SG matrices. So you can see that how weak the condition about the samples are in terms of like not including vertices and so on. So under this condition, we can show that the solution of the Det-Max criterion will be providing us the original factors with some, in this case, there's no sign ambiguity because we have the non-negative constraint with some ambiguity in the permutation. Okay. So we will actually tie this criterion to some information-theoretic criterion later, but it's essentially from the geometric point of view, we are trying to spread our samples inside the polytope, knowing that original samples are spread sufficiently inside the polytope. So that's the main idea. So if we review the polytopes that we covered up to this point, we actually covered 3 polytopes: L infinity norm ball, L1 norm ball, and non-negative L1 norm ball. We have also intersection of the L infinity norm ball with the non-negative orthants, which we refer to as non-negative anti-sparse case. So for all of these, we can give such theorems: sufficiently scattered assumption leading to identifiability. The next step, so this was actually our research route. So we were looking at the sampling conditions. Then we said, okay, for these 4 polytopes, we can show identifiability. Can we do it for some other polytopes? Or are these just special polytopes like the, I don't know, Platonic solids or something? So this is, but the answer turned out to be actually, we can find infinitely many such polytopes. And that's the main results about the polytopic matrix factorization, which I can happily call fundamental theorem of PMF. So this again, with my student Gökçen, it's actually proof is up to Gökçen. So this is, this theorem is saying that if the polytope is satisfying certain symmetry restriction, then basically it leads to an identifiable PMF framework. So under the condition that you have sufficiently scattered samples. So, and the restriction is only symmetries that you allow are basically permutations, which means you switch, for example, S1 with S2, but the polytope shape remains same. Or sign alterations, you basically change each component with its negative, some of the components maybe, but the polytope remains same. So you allow such symmetries, but you don't allow other symmetries. For example, for a 3-dimensional case, for example, you turn it like 30 degrees or something, you get the same polytope, then it's not an identifiable polytope. So I'm glad that symmetry somehow popped up here in the some fundamental result about the linear inverse problem. But you may question, like, what is the use of such infinite choices of polytopes, right? So if you think about it, up to this point, we have like 4 or 5 sets that we know that enable identifiability in the linear inverse problem. Now we actually extended to infinitely many sets. And in terms of the unsupervised problem, that gives us great flexibility in latent vector characterization. And I will try to explain it in terms of an example, but the key thing is that we can impose feature properties in the local level. So in the subvector level, instead of defining the feature attributes in the whole vector level. To basically illustrate that, let's consider this 3-dimensional polytope for just illustration. So its first 2 components are signed, and the third component is constrained to be non-negative. Okay, so this actually gives us this heterogeneous feature structure that we impose non-negativity only at the local level. We don't really require that all of the samples are non-negative. We allow some of the samples or components to be, I shouldn't say samples, the components to be signed, some of the components to be non-negative. And also I impose sparsity constraint, again in the subvector level. I only say that x1 and x2 are mutually sparse, x2 and x3 are mutually sparse. I don't really impose that x1, x3 are sparse, mutually sparse, or basically the whole vector is coming from a 3-dimensional L1 norm ball. Okay, so, and if you look at actually the polytope, its shape looks like this. And if you do the search, it turns out to be an identifiable polytope. So it basically satisfies the symmetry restriction. So therefore, with such a polytope, we are able to define a heterogeneous feature vector, latent vector, with only some of the components are non-negative, some are signed, and basically some sparsity is imposed at the subvector level, right? So that is the flexibility in terms of defining latent features. And in terms of solving this Det-Max problem to obtain this H and S matrices, we can introduce actually two different approaches, batch algorithms versus online algorithms. Batch algorithms are basically using whole Y matrix and basically try to find H and S matrices, doing iterations over the all H and S matrices. And we can use actual coordinate ascent algorithms for that we can borrow from actually the NMF literature, which basically optimize for H, then follow it by optimization by S, doing gradient update type searches. I'm not going to go into the details here. So there are Nestorov type improvements in terms of speed and so on. It's a non-convex problem, but you basically typically obtain the H and S matrices in the empirical way by solving this problem. Alternative approach is using online algorithms, which actually lead to neural network implementations. So that is, I guess, the interesting part. With actually another interesting part is that the activation functions for these neural networks turn out to be piecewise linear functions, such as value clipping functions and so on. And this work is actually my joint work with my students, Berfin and Merve. Berfin was an undergraduate student here. So here in the online algorithms, you essentially have a causal constraint in the sense that you assume that the inputs are coming, basically the YKs are coming in time with some order, and you are basically producing output as the inputs are coming in. So for that purpose, we introduce actually a running correlation matrix for the outputs, which we are trying to maximize the determinant. But we use a weighting here, which has this lambda factor here, exponential weighting, where the lambda is some quantity close to 1, but less than 1, which is actually the forgetting factor. The reason we introduce this factor is that in the convergence of this online algorithm, initial SKs are not reliable. So they're not really the correct SKs. So we don't really want the previous initial SKs to affect our correlation calculation later. And furthermore, we can actually use this for the non-stationary data models. In some applications, H can be changing. I will illustrate that. So we want our basically algorithm to adapt to changes in the data structure. So the generative model may be a dynamic model. So we may want to track that using such a model. So this is basically the correlation matrix, exponentially weighted correlation matrix. So we introduce the online version of our algorithm through such a basically optimization at each step. We try to maximize the log determinant of RSK. We replace hard constraint that the inputs are equal to basically H times the output with actually inequality, because S and H at any stage are not perfect because we are in the learning process. So therefore, we try to keep HS in the vicinity of YK rather than being equal to YK. And SKs are constrained to be inside a polytope. So that is basically our assumption. So we can actually move the first constraint, inequality constraint, to here by multiplying with the Lagrange multiplier beta and put our optimization in this form. I will skip some details because I have limited time, but if you do the gradient ascent with projection to the polytope, for the gradient ascent, you have two components of the cost function. First part is basically input reconstruction. You are trying to reconstruct input from the output. And this component is basically trying to spread the output within the polytope. Okay, so we have these two components. So you got the gradient of the log determinant part and the gradient of this part, where this epsilon is basically your error that you make in reconstructing the input. For the log determinant, the derivative is the inverse of its argument, inverse of the matrix argument. So it's the correlation or covariance. We can actually use covariance too. Inverse of the correlation matrix that we build up to that point. So we call it as the B matrix. So we need to actually keep account for not for the correlation matrix, but for the B matrix, which is the inverse of the correlation. And since the correlation satisfies a rank 1 update, we can use matrix inversion lemma to also obtain a rank 1 update for the inverse of the correlation. Okay. So if you look at the gradient ascent for example, for the infinity norm ball, if you do the gradient search for the S vector, you can write it as a actually solution of a differential equation. So you can put it into form of a differential equation form, where V is the updated gradient updated vector, and then you project V to the L infinity norm ball. And projection into the L infinity norm ball is actually simple. You just clip. If the component, any component is greater than the boundaries, you basically clip it to, let's say, -1 to 1 region. So, and you can actually manipulate the expressions. That's called a Hopfield trick, so that it satisfies the form of a leaky integrator. M here comes from the inverse covariance matrix, and H is basically our H matrix. And this is the dynamics of our neural network. And these are the actually synapse updates of our neural network. One thing, so let me actually show the neural network corresponding to this. It is actually a 2-layer network, and it has this output neurons. In my room, there's no light now. Okay, so these are my output neurons, and clipping activations are due to the fact that we are basically using infinity norm ball as our polytope. And we got 3 types of actually connections, which are basically feedback. These red ones are feedback. So these neurons are actually, we are trying to predict input with our output. So these red connections are for those predictions. And these are basically calculating errors that we make in predicting inputs. Okay, so the outputs of these neurons are basically prediction errors. And so these are top-down connections, red connections, which sort of actually fits to assumptions about the neural, biological neural systems, which are believed to have these top-down connections for sensory signal predictions from the higher level cognition levels signals. So this is a top-down connection, and we propagate the error to the output neurons to update our neurons. So that's the feed-forward connection. And we have this lateral connection between the output neurons. So these are the recurrent connections, and they come from the inverse covariance, and their goal is to maximize the determinant of the covariance matrix. Okay, so they actually make sure that our output is using the whole n-dimensional space. Okay, so they basically avoid degeneracy at the output and try to spread the samples inside the polytope. So one important thing is that these updates here are local updates, which means that, for example, this synapse here is updated only by the activation of this neuron and activation of this neuron. So there's no other neuron inside our neural network that is affecting this synapse. So that's a good thing in two domains. It can be actually considered as a candidate for mathematical models for biological neural networks because they have this locality constraint. Another thing is that the neuromorphic chips that use basically analog-based neurons, they are constrained to use local algorithms. So they cannot use something like backpropagation to update such synapses. Okay, so that basically, that comes out of, I'm not really imposing any network structure or any learning rule. They come out as basically result of the optimization process. So if we consider actually B1 plus, which is the non-negative sparse case, again, I'm not going to go through the dynamics, but you can see that the projection algorithm to B1 plus is more involved actually. It requires a proximal operator, which uses the ReLU function, actually soft thresholding, but if we combine with the non-negativeness, we obtain the ReLU. So the activations in this case are rectified linear units with the bias that is determined by this additional neuron that basically takes the outputs and generates a bias signal for them. Okay, so this is like a giant inhibition neuron that basically tries to generate a bias for all of these output neurons, so that basically you got these sparse activations. You are moving this threshold levels for those rectified linear units to generate that. Just to illustrate the use of this sparse case, this is like the fruit fly problem of sparse coding, which is due to Bruno Olshausen and Field. So this is basically the natural images. You take like 12 by 12 sections from these images and feed it to a sparse component analysis algorithm. And in this case, we feed it to our network, which uses these local updates. And then if you look at the H matrix columns, you obtain this basically images, 12 by 12 images, which corresponds to Gabor-like wavelet structures. So they basically are edge detectors. So they come out of this unsupervised learning process, and it's basically observed in primate cortexes, right? So this is actually for example, in humans, it's actually first discovered in cats by Hubel and Wiesel. So this back region of the brain is the primal visual area of the brain, where basically there's entrance of the optical fibers, first enters into thalamus and then comes to cortex in this region. And there's a region called V1, it first entrance region into the primal visual cortex. And if you look at the receptive fields, you see very similar patterns for these neurons. Another application, again, in the brain domain. So here we are trying to do brain imaging using basically EEG, which basically puts some electrodes around the scalp, and you basically essentially measure the voltage variations across the scalp. Because of the brain activity, there's a voltage variations. Brain activity is essentially an electrical activity or electrochemical activity. So that generates different voltage patterns around the scalp. So if you look at those voltage patterns that you obtain across time, so in this picture, this is the nose. So we are looking from the top. these are ears. So this is the heat map. So you can see that the voltage is high around the back of the head here, and then, so it basically changes across time, but you can say that it is distributed around the head because there are different sources active inside the brain at a given time. So we want to actually separate them using an algorithm to basically look at, like, so these are our measurements. So we are trying to write our measurements in terms of some of these localized sources, dipolar sources. Okay. So these would correspond to different brain sources, and these are their activations. So if we, I mean, there are some pre-processing stages that I skipped. We take basically some frequency bands and then feed those inputs to this basically B infinity neural network here. Polytopic matrix, online polytopic matrix factorization neural network. We obtain this picture. I will actually show you a animation for that. In this animation, you see basically how the components evolve as the inputs are coming in. So potentially, there's actually in this, it's a cognitive experiment that things are changing. So different brain regions are getting active and so on. So here, these are the basically scalp voltage distributions for components that we obtain. And this is the time frequency distribution. So this is the time axis, this is the frequency axis for each component. And the frequencies are going till 0 to 40. There are different basically meanings and names assigned to different regions, but I'm skipping that. So if I basically run this, you can see that the components are changing, and you can see some frequency localizations in different regions of the brain. So you basically obtain different components. So from these, our goal, we are still investigating this, is to identify which parts of brain are correlated to which cognitive activity and so on. So that is, so that's some work in progress that we are actually still investigating. So I guess this is actually the part about the polytopic matrix factorization. And then I will sort of briefly talk about information-theoretic perspective for the unsupervised learning. And the thing is that we want to actually look at this Det-Max maximization process from the information-theoretic point of view. In terms of information, Shannon basically introduced this entropy as a measure of basically uncertainty of a random variable, or the information content of a random variable or a random vector, and the mutual information between two random vectors. So this information measure is used in independent component analysis by Bell and Sejnowski to actually obtain the components. So they posed the problem as Y is the input, S's are the outputs. So we try to maximize the mutual information between the input and output, assuming that S's satisfy certain marginals, and also they are basically independent. So given that you make the independence assumption, makes actually this information maximization principle relatively easy, because you are not dealing with the joint density of these outputs. You are just dealing with the marginal densities, which are reflected by these the nonlinearities G, which are related to the CDFs of these random variables. So if we want to carry this information maximization principle to the case where there's no independence assumption, then things become hard with the Shannon entropy, because you need to actually have a characterization for the joint density of the output, where you are not able to assume that it's a separable PDF. So instead, we used an alternative entropy measure, which is, we call it as the LD entropy or log determinant entropy, which is nothing but actually the Shannon entropy of the Gaussian random vector, slightly modified with epsilon identity here. That's for actually some numerical reasons during the adaptation process. So, but we use this irrespective of the actual distribution of these S vectors. So, so it's actually a second order statistics-based entropy definition. And here in this world, the inference is basically by linear minimum mean square error estimation. So, so this entropy definition, when epsilon goes to 0, S is a Gaussian variable, matches to the Shannon differential entropy for the Gaussian. But as I said, we are just using it for irrespective of the actual distribution of sources. So what we are trying to do is we are trying to come up with a new information measure or alternative information measure, which is relying on the just second order statistics and the domain information of the vectors, so that we can do this mutual information maximization. So we can actually write this mutual information in terms of these LD entropies, where this entropy here is the entropy of errors that for predicting Y's from S's linearly using MMSE estimation. Okay, so this is not the usual conditional entropy. So this is basically the inference is implied inference is the linear MMSE inference. So I will skip some details due to the time limitation, but for this mutual information measure is also non-negative, and it's 0 when the covariance is equal to, cross covariance is equal to 0. Okay? So it's a measure of uncorrelatedness rather than independence, as in the Shannon mutual information case. One thing that I want to say about the sufficiently scattered samples, these sufficiently scattered samples has the property that they form a maximal entropy subset of the polytope according to this definition, in the sense that no linear transformation that maps them inside the polytope can increase their entropy. Okay. So that's why I call it as the maximal entropy rather than maximum entropy, because all of these sufficient scattered sets can have different entropies. So we pose our information maximization approach as transfer maximum information to the outputs, given that the outputs are constrained to lie inside the polytope, according to this information criterion. So skipping some algorithmic details, if you consider uniform correlated random variables, so inside this L infinity norm ball, using a Coppola distribution, here the bottom axis is basically the x-axis is the correlation level among these components. If you apply the ICA algorithm, this is essentially the success measure, signal to interference ratio. So it basically degrades with the increasing correlation as expected, because it assumes that the components are basically independent, uncorrelated. But the LD Infomex approach basically has this black one is basically the utopia case, assuming that you know the H matrix. So again, is close to that, but it drops a little bit. This is due to the fact that we are using just finite samples, and due to high correlation at those high correlation regions, the satisfaction of the sufficient scattered assumption basically is violated. But if you increase the size of data samples, it would improve. And just to show another example, these are 3 images from my personal library. If you mix them, this is a blind source separation example, and then apply ICA Infomex, you got these actually ghost images because the separation is not perfect. I will explain the reason. But if you apply the LD Infomex, it's actually much better. There's actually a small ghost of this both here. There's still some actually interference, but it's not as bad as this guy. So this is due to the fact that if you look at the empirical Pearson correlation between these two images, it's like 0.41. So they're really correlated with each other. So as the extensions of this work, one thing that we are excited about is applying this LD Infomex principle to self-supervised learning. So we are actually together with Deniz Hoca and actually majorly with our students Serdar Özsoy and Shadi Hamdan and Sercan from the Google, we are trying to apply this and getting actually some good results for applying to self-supervised learning. So this is actually a TSNE picture for the CFAR10 case that we obtained from the self-supervised learning. So we basically train in an unsupervised way so that using this LD Infomex criterion, we are trying to spread the samples. At the same time, we are trying to get related sample close to each other. And then you use a linear classifier to supervised classifier to learn. So that's an extension that we are working on. I will skip this communication extension. And with actually my student Barışcan, we have this recent paper identifying the polytope. Whether it's identifiable or not, it's a permutational complexity problem. But Barışcan actually developed a very wise approach looking at the generating set of the automorphism group of the polytope so that you can just do checks on that. And it's actually practically reduced. So if you look at this, this is the computational time if you do the permutation check. So it grows with the number of vertices of the polytope very easily. But if you apply the Barışcan's method, you got actually a fairly reasonable, you can determine identifiability in a fairly reasonable amount of time. I guess I'm a bit, I'll skip this. So we have other extensions to development of neural networks using this Polytopic Matrix Factorization, which leads to actually different neural networks with local learning rules. I guess I should stop now. I'm already over my time, I guess. I'm happy to take any questions you may have.
Thank you, Alper Erdoğan. Yeah, we are open to questions from our audience. Maybe I can start. Thank you again,
Sure.
Alper Erdoğan. So this Det-Max criterion that you used in your formulation reminded me of what we call determinantal point processes, which is a framework in machine learning, which deals with a somehow a different problem. We have a fixed, typically a large number of data items, and using objectives similar to this one, it can give us both diverse subset of elements that can also have some sort of high coverage by looking at the kernel matrix defined between the objects. In your case, is it somehow the same? You said that you are spreading the samples through the volume, but can you also guarantee that it also maximizes the coverage as well as the diversity?
Coverage in the sense of the original domain coverage, or?
Coverage in the sense that, like, if you suppose that you have a fixed number of elements in your subset, and you are trying to select another sample from your ground set. So it should just give you a more probability defined over the subset of the ground elements. So maybe I can also share this with you. For example, in your visualizations on these learned bases from these patches of images.
I see.
So for example, can you identify that some of these are somehow similar to each other, or they completely different orientations?
In this case, this is not over complete case. So this is actually a basis essentially. So you cannot really produce one from the other one, I guess, if that's your question, right? Is it the so in the over complete case, I guess, if you are using a dictionary where H is actually a fat matrix, in that case, I guess that condition can be checked. But since this was actually a square matrix, we haven't really, I'm not really actually aware of trying to write one dictionary element in terms of the other components. And so that's coverage.
So again, DPP is solved a completely different problem, but I just solved some sort of similarities. So maybe I can also share a relatively old survey paper. Maybe you would like to take a look. Okay.
I would like to ask something not related to information theory. I'm sorry, were you finished? I could maybe I.
Yeah, I'm finished. Okay.
I was attracted to your talk with the idea of the factorization. I used to do work on molecular dynamics where there are thousands and thousands of degrees of freedom, but not all of the modes participate in the dynamics. That's the similarity with information theory also. Not when you transmit my voice, a lot of the frequencies are junk, so they do not participate. So I used to try to find ways of dropping the degrees of freedom and keeping maybe 5 to 10%. So that's why I was attracted by your title of factorization. In my kind of work, if you could factorize, you would drop many of the matrices that form the bigger matrix. But then the question is, which ones to drop so that you can keep the essence? I looked a little bit at information theory work at that time. I'm talking of 20 years ago.
I see.
But I wasn't able to is there such possibility of selecting the piece that is important and dropping the rest so you can work with a much smaller system? Otherwise, it takes thousands of hours of computation time and nobody.
Is one of the application, so one of the application areas of the matrix factorization is actually this low rank decompositions, where you say that it's the measurement space is actually the actual dynamics behind the measurement space is low rank feature vectors that you obtain. But what you actually say is a dynamical system lower dimensional representation, which is actually sort of another problem. So there are like ways to represent systems, linear systems, or maybe nonlinear systems, which are represented by state space representations, and you try to actually squeeze their states to a lower dimensional space by describing some measures which, for example, you try to match the frequency responses of basically lower dimensional state space representation and so on. But that's not really directly relevant to what I do here. Actually, this is a little more simple than such dynamical system dimension reduction methods.
Well, thank you. It was an interesting talk anyway. But
thanks a lot. Thanks a lot, Roberto John. Thank you.
Actually,
Okay.
I have a quick question, Alper Hocam. Thank you. There were a lot of interesting results also. Thanks for the presentation. One particular thing that I have in my mind is when you have the data, the Y matrix that you want to decompose into with this new polytopic constraint, to what extent we can generalize this to some sort of, let's say, in the high dimensional setting? Do you have any findings around that? Because when we have the, let's say, the ambient dimension that grows, we can simply extend to an extent. But then if you switch into the random matrix theory setting in which both dimensions grow by some fixed ratio, potentially we are going into a different field where everything like has a concentration along not only necessarily on this polytopic constraint, but on the shallow region, which is known as let's say RMT setting. Do you have any idea along this line in the high dimensional?
Actually, we are interested in such concentration issues, or actually blessings, I should say. We look at it as in terms of some gain potentially. If you consider the polytope in the high dimensional case, as you said, the volume is going to be mostly will concentrate towards the borders, right? So therefore, this satisfaction of the sufficient scattered condition is potentially be more likely. So I expect that we don't have a result for that. We are searching for a result actually. So a phase transition like thing in terms of how many samples we should have to satisfy the sufficient scattered condition in such a high dimensional scenario. So if you consider those samples inside the polytope, and then the thing that we are interested in, we have actually some partial results for the self-supervised case, for the communication signals, for the massive MIMO setting, where we can actually give some phase transition for the number of unsupervised samples, but the dimensions that we are talking about is not, I mean, very high. The measurements are like 1,000 dimensional, assuming 1,000 antennas and 40 users or something like that. But we can give phase transitions for both the training component as well as the packet length, which is the unsupervised component. But it would be interesting to actually obtain general concentration results for any polytope as a function of how many samples you need to satisfy the sufficient scattering condition, so that your samples convex all contain the maximum volume inscribed ellipsoid.
Nice. And also for the online learning regime, you are always in the finite setting, right? All the results we have seen, you are not covering like what happens in the case of the high dimensional setup.
Can you clarify that? What is the, when you say dimension?
When you switch into the covariance that you use in the online case, it becomes, let's say, unrobust to kind of estimate, but in the, let's say, due to some recent findings in the both RMT side and also in high dimensional inference models. But I kind of see that in your online polytopic, I think it was in one of the first few models that you introduced, you were introducing the online case just by some, okay, yeah, where was it?
It's the one?
Yes, so
the correlation matrix.
The correlation, exactly, yes, here. So the dimensionality of S and the number of samples.
I see.
Your assumption?
I see. Since when the S vectors are high dimensional, the R would be initially the basically ill-conditioned, you're saying, right?
Yes, so and potentially like a Martian capacitor will kick in. That is what I'm
exactly. So we actually start with a full rank, say, diagonal R matrix. Actually, we start with a B matrix. We are not really updating R, we are updating B. So we initially start with prior on B, and then update it using the data vectors. So therefore, I mean, if you are not careful about the lambda values you're choosing, you may run into such extremely ill-conditioned problems. So there's actually some lambda parameter selection, but I mean, the dimensions that we tried is, for example, for the image cases, like 144 dimensional vectors and so on.
Thank you, Alper Erdoğan.
Thanks, Zafer Hocam.
So, yeah, we are a bit over time. I think we can stop here again. Thanks, Alper Hocam, for this
Thanks
really
all.
interesting talk, and see you all next week.
See you.